Hello students, welcome to EPG Pathshala. I am Dr. Sanjay Kumar Chamoli from Department of Physics and Astrophysics, University of Delhi. Today we are going to discuss about the module Nuclear Models Part 7 from paper Nuclear and Particle Physics. After studying this module, you will be able to understand number 1, the basics of shell model, number 2, knowledge of magic numbers in nuclei, number 3, the finer details of the shell structure in nuclei. Shell model applications, spin. In this particular slide, we are going to study that how the ground state spin is predicted by the shell model in case of odd nuclei. Now for even a nuclei, even A means what kind of even A? In which n is equal to odd, z is equal to odd. There is a rule which basically gives the ground state spin in those nuclei. And that rule was given by W.L. Nordem in 1950, which is usually called Nordem rule. So Nordem rule for most probable value of spin in odd nuclei. Now what is Nordem rule? Now in order to define the spin value in odd nuclei, Nordem basically defined a number which is called the Nordem number, which is Nn is equal to Jp minus Lp plus Jn minus Ln, where J and L are the total angular momentum and orbital angular momentum, and P and N corresponds to protons and neutrons. So for any odd nucleus, we want to see what is the orbital in which the odd proton is there and what is the orbital in which the odd neutron is there. Then corresponding to these two, then looking at those orbitals, we can put the values of Jp, Lp and Jn and N, and then find the Nordem number. Then looking at the Nordem number, there are two possibilities. Number 1, if Nn is equal to 0, then the ground state spin for that particular nucleus is given by J is equal to mod Jp minus Jn, which is called strong rule. In the other possibility, if n is equal to plus minus 1, then J is equal to Jp plus Jn or J is equal to mod Jp minus Jn. This rule is called weak rule. Shell model applications, spin. In this slide, basically we are going to discuss the application of shell model in terms of determining the spin of the ground state spin of various nuclei. In this slide, a table is given in which various details of various nuclei are shown. So the different columns are nucleus, proton number, state, neutron number, state, Nordem number, J predicted and J experimental. So basically here in this case all odd nuclei are basically discussed. For example, in neutron 14 neutron, number of protons are 7, number of neutrons are 7. The protons, the last odd proton is basically is in the p half orbital, the odd neutron is in the p half orbital. Nordem rule predict that the Nordem number has to be -1. So its spin can either be 0, total spin can either be 0 or 1, and experimentally the spin observed is 1 plus. Similarly for potassium 42, Z number is 19, N number is 23. So the 19th proton is in D3 by 2 orbital, 23rd neutron is in F7 by 2 orbital. According to Nordem rule, the Nordem number should be 0 and the predicted spin for 42 potassium is 2, whereas the experimentally observed ground state spin of 42 potassium is 2 plus. Similarly, barium 80 and 208 thallium cases are being discussed, and the predicted spins are found to agree with the experimentally observed spin and parity. Shell model applications, spin. Now, up to previous slide, we have discussed the application of shell model in predicting the ground state spin and parities. But the applications of shell model are not only limited to the ground state, but excited state spins and parity can also be predicted using shell model. Here in this slide, an example of oxygen 17 is given. Its various nucleon distribution in various states, various energy states are shown in the ground state as well as in the excited state. Now, in the ground state, oxygen 17 has the spin and parity as 5/2 plus, and it is basically clear from the energy level diagram that the odd nucleon is in the d5/2 orbital. Now, when we talk about the excited states of oxygen 17, then basically we can discuss three different scenarios. In the first scenario, the proton from 1p/2, 1p half orbital is excited to 1d5/2 orbital. So, in this case, there are three odd particles. One proton odd particle, one odd proton is in d5/2 orbital, one odd proton is in p half orbital, one neutron is in d5/2 orbital. So, three odd particles are there, and in this case the ground state configuration can be written as pi 1d5/2 1 1p half minus 1 into nu 1d5/2 1. Another scenario is one neutron from filled 1p half orbital is excited to 1d5/2 orbital. So, now in this case the two neutrons in the d5/2 orbitals will be coupled, but there is a hole in the p half orbital on the neutron side. So, corresponding configuration for this excited state will be nu 1p half minus 1, and since the odd neutron is occupying the 1p half orbital, so the excited state spin and parity as per the shell model will be j pi is equal to 1/2 minus. In the third scenario, the odd neutron in the d5/2 orbital is excited to 2s half orbital or 1d3/2 orbital, because 2s half orbital and 1d3/2 orbitals are very close in energy. So, the odd neutron, that is the 17th nucleon in oxygen 17, can be excited to either 2s half orbital or 1d3/2 orbital. So, depending upon whether it has been excited to s half orbital or d3/2 orbital, there can be two spin states possible. If it is excited to s half orbital, then the excited state spin of oxygen 17 will be j pi is equal to 1/2 plus half. Or if the odd neutron is excited to 1d3/2 orbital, then the expected excited state of oxygen 17 will be 3/2 plus. So, corresponding to these two possibilities, there will be two different configuration. When the excitation is in the s half orbital, the correct configuration, the proposed configuration is nu 2s half 1, and when it is excited to d3/2 orbital, then the excited state configuration will be nu 1d3/2 1. Now, when the excitation of oxygen 17 takes place, either of these three situations will happen. So, we would like to see which one of them is more probable. Now, if we see how much energy is needed to make these excitations, then it turned out that the excitation energies or the energy required to excite oxygen 17 via these three modes varies in terms of, in the third one is less than 2 is less than 1. So, it means it is very easy to excite the oxygen 17 nucleus via third mode. Then the second preferred mode is second mode and the least preferred mode is 1. That is understood because in the third case only one neutron, the odd neutron, has to be excited. In the second case, the pair of nucleons from p half orbital needs to be broken and the odd neutron has to be excited to d pi by 2 orbital. Whereas in the first case, the proton pair needs to be broken and then the odd proton goes to d pi by 2 orbital. Now, it is very difficult to break a proton pair as compared to neutron pair because of an additional interaction, that is Coulomb interaction. Shell model applications, magnetic moment. So, now in this slide we are going to study that how shell model can predict the magnetic moment values in various nuclei. Shell model can predict magnetic moment in nuclei. What is magnetic moment? Magnetic moment mathematically is defined as mu is equal to mu n into G into I, where mu n is nuclear magnetron, G is equal to G factor, which is also called the Lambda G factor, and I is the nuclear spin. For even nuclei, since the ground state is 0 plus, that is I is equal to 0, so magnetic moment mu has to be 0. So, magnetic moment is 0. For odd nuclei, magnetic moment is only due to the odd nucleon. So, odd nuclei means the nuclei in which either Z is odd or N is odd. In that case, the magnetic moment is only due to the odd nucleon. Why it is so? Because odd nuclei can be considered as equivalent to even nucleus plus even nucleus plus one nucleon. For odd nuclei, magnetic moment is the vector sum of magnetic moments due to odd proton and odd neutron, that is mu is equal to mu p plus mu n. Shell model applications, magnetic moment. Now, in this slide, basically the application of shell model is discussed in determining the ground state magnetic moment of nuclei. For odd nuclei, the magnetic moment is given by mu is equal to Gj mu n, where G is called the gyromagnetic ratio, J is the spin of the nucleus and mu n the nuclear magnetron. For proton, Gl is equal to 1, Gs is equal to plus 5.5856. For neutron, since there is no charge, so Gl is equal to 0 and Gs is equal to minus 3.8262. It means the magnetic moment associated with proton and neutron will be oppositely directed. Now, in the arrangement when J is equal to L plus S, the magnetic moment for odd nuclei is given as mu is equal to Gl I minus half plus mu s, and in the arrangement when J is equal to L minus S, the magnetic moment, the ground state magnetic moment for odd nuclei is given as mu is equal to Gl I minus bracket mu s minus Gl by 2 bracket close bracket I upon I plus 1 bracket close. Now, these two are the extreme values of magnetic moment for the two cases when J is equal to L plus S and J is equal to L minus S. These values are called the shell model values or the theoretical values, and they are better known as Schmidt values. Shell model applications, magnetic moment. So, we are continuing with our discussion about the applicability of shell model in determining the ground state magnetic moment of nuclei. We are discussing the case of odd nuclei. So, here in this slide, basically two pictures are shown. One picture on the left hand side is odd proton. On the right hand side picture, we have for odd neutron. So, in the picture on the left hand side, in both these picture, the magnetic moment is represented in terms of nuclear magnetic moment, in terms of nuclear magnetron as a function of nuclear spin in the unit of h bar. Now, on the proton side, we find that the two lines, more or less parallel lines, represent the Schmidt values for the cases. The upper line indicates the case of j is equal to L plus half. The lower one indicates the case of j is equal to L minus 1, L minus half, and we find that these are the extreme values, whereas the observed values for most of the nuclei fall within these two lines. It means the experimental values are found to be different than what they should be as per the shell model, or we can say that the experimental values fall within these two limits. There are only few exceptions where this rule is basically not followed for odd proton nuclei. Whereas, if we observe the right hand picture, which is for odd neutron nuclei, we find that upper solid line represents the case of j is equal to L minus half. The lower line, which is a straight line, represents the case of j is equal to L plus half. We again find that the experimentally observed magnetic moment for odd neutron nuclei fall within these two lines. So, it means that Schmidt values or the shell model predicted values basically define the limiting cases of magnetic moment for various nuclei. Shell model applications, magnetic moment. So, we still continue with our discussion about the application of shell model in predicting the magnetic moment of nuclei. Now, in this slide, we are going to discuss the case of odd nuclei. Odd nuclei means in nuclei where the Z number is odd and N number is odd. For example, nitrogen 14. Nitrogen 14 has 7 protons and 7 neutrons. In odd nuclei, magnetic dipole moment is the vector sum of magnetic moment of the odd nucleon. That is, mu is equal to mu 1 plus mu 2, where mu is equal to Gj into mu n. Now, for two different situations, when the proton and neutron spin, the odd proton and odd neutron spin are parallel, in that case, G is equal to 2j minus 1 bracket close Gl plus Gs upon 2j for j is equal to L plus half, and G is equal to 2j plus 3 Gl minus Gs upon 2 into j plus 1 for j is equal to L minus half. For proton again, Gl is equal to 1, Gs is equal to 5.5856. For neutron, Gl is equal to 0 and Gs is equal to minus 3.8262. Shell model applications, magnetic moment. Here in this slide, various examples have been discussed. For example, the case of deuteron. For deuteron, there is one proton and one neutron. So, both odd proton and odd neutron, they are in the 1s orbital. For s orbital, L is equal to 0. So, here L is equal to 0. So, we would expect mu is equal to mu neutron plus mu proton, that is equal to minus 1.91 mu n plus 2.79 mu n is equal to 0.88 mu n. So, this is the shell model predicted value of magnetic moment for deuteron, but actually in the experiment the value obtained is 0.86 mu n. So, we can say that the shell model value is very much close to the one that is experimentally observed. It shows the great applicability of or great success of shell model in explaining the magnetic moment of odd nuclei. Now, again in the second case, that case of tritium is discussed. In tritium, the chemical symbol is 3H. So, it has got one proton and two neutron. Again in this case, L value is 0 because the odd proton is in s orbital, the two neutrons are again in the s orbital. So, here since the two neutrons will be paired up, so there is no contribution of them, but only the contribution of proton will be there. So, expected value of mu is equal to mu proton, that is 2.79 mu n, and the experimentally observed value is 2.78 mu n. So, again it is a very nice agreement between the shell model calculated value and the experimental value. In case of helium 4, there are two protons and two neutrons. So, protons are in the s orbital, neutrons are in the s orbital. So, since protons are coupled, they are paired up in s orbital, the total spin is 0. Two neutrons are in the s orbital, they are also coupled, total spin is 0. So, expected mu is equal to 0, and actually in the experiment the value obtained is also 0. So, it shows that shell model can predict the ground state magnetic moment in odd nuclei also. Shell model applications, quadrupole moment. In this slide, we will discuss the shell model applications in predicting the ground state quadrupole moment in nuclei. Now, electric quadrupole moment, as we know, show deviation from spherical symmetry. It means if a nucleus has quadrupole moment, it suggests us that the nucleus is not spherical. Neutrons have no charge, so do not induce quadrupole moment. Now, quadrupole moment by definition is due to the asymmetric distribution of charge. Now, as neutrons do not have any charge, so they cannot induce the quadrupole moment. For nucleus with single unpaired proton, the quadrupole moment is defined as Q is equal to minus expectation value of R square, where expectation value of R square or the mean value of R square is equal to 3 by 5 R square is equal to 3 by 5 R0 square e to the power 2 by 3 is called the mean square radius of nucleon in the orbit, where R0 square, R0 is the constant and A is the nuclear mass. So, quantum mechanically the expectation value of quadrupole moment as per the shell model is equal to minus 2j minus 1 over 2 into j plus 1 into mean square radius. Shell model applications, magnetic moment. So, we continue our discussion about the magnetic moment. Here in this slide, basically on the right hand side we have shown two pictures. One picture, the upper one corresponds to odd proton, other picture corresponds to the lower one corresponds to odd neutron. What we have plotted here is the magnetic moment values for various spin values on the x-axis, and on the y-axis we have the magnetic moment values. So, here basically you can see that ideally a nucleus with an odd neutron should have no quadrupole moment, because neutron is odd and quadrupole moment is nothing but the asymmetry in the charge distribution. Since the neutrons do not have any charge, so ideally speaking the nucleus with odd neutron should have no quadrupole moment. But in actual, the neutrons in nucleus interact with nucleons of core to polarize it and generate quadrupole moment. So, in actual practice we see that some quadrupole moment is there for odd neutron nuclei. So, students, let us summarize what we have learned in this module. As we have seen that in this module we have came across very many concepts, but what is the final outcome? How we have enhanced our learning? So, the first thing that we have learned in this module is that the shell model can explain the spin and parities of states in nuclei. Second thing, the shell model can explain the observed magnetic moment in nuclei. Third, the shell model can explain the observed quadrupole moment in nuclei. Also, we have learned that the shell model can predict the excited state spin and parities in nuclei. And finally, what we have learned is shell model can predict electromagnetic moments in nuclei well.